In today's video, we'll be focusing on limits when x approaches infinity or negative infinity. Where you saw that last year is that was your horizontal asymptotes. So first off, can the horizontal asymptote be crossed? And the answer should be that it's true. It can be crossed. You saw graphs last year when you did rational functions that looked something like this. And often, maybe you had a section like this here, you had a section like that there, and you had a section in the middle that might have crossed the horizontal asymptote. So horizontal asymptotes can in fact be crossed. Vertical cannot, but horizontal can. What the horizontal asymptotes are, they are the values that if you go really far out to the left, so in other words, as x approaches negative infinity, or really far out to the right, which in other words is x approaches positive infinity, those are the values that you are getting closer and closer to. So the horizontal asymptote is really just telling us something out to the far left of the graph and the far right of the graph. Now, how many horizontal asymptotes can a function have? Last year, you pretty much looked at ones that had one horizontal asymptote. But what we'll find out today is we can, in fact, have up to two horizontal asymptotes, because the value that you approach as you go to negative infinity will sometimes be different than the value you approach when you go to positive infinity. The video today is going to work through pages in the packet, so we'll be starting on page 5 in the packet. And what you're going to do is you're going to pause the video and for a few minutes fill in this chart for the function that we have above. Now they have this labeled as a of x, so we're going to switch this to a of x here. So you're going to plug in your x values, just see what you get back for your y values, and then you'll plot those on the graph below. So you can pause the video and take a few minutes to do that. Okay, so when we had x values that were getting closer and closer to positive infinity, heading to the right on our x-axis, when we went 0, 1, 10, 100, 1,000, you should have noticed that things were getting closer and closer to 3. Same idea when we put in the negatives. They were getting closer and closer to 3. And when you graph it, you can see that it is leveling off at a y value of 3. So that means our horizontal asymptote is 3. If we talked about this with limits, we would say the limit as x approaches negative infinity of a of x is equal to 3. And we would say our limit as x approaches positive infinity of a of x is also 3. And that's what we'll be focusing on today, looking at limits in this notation as x approaches negative infinity or x approaches positive infinity, which is just really a different way of talking about our horizontal asymptote. Now in question 3 here, how you would have found this last year, we have the same degree. We have an x squared over an x squared. If you have the same degree, you saw that you just divided the leading coefficients to get the horizontal asymptote. Well, that's really 3 over 1, so that would have given you the y equals 3. Now, in general notation, this here down in number 4 would be read as the limit as x approaches infinity of f of x equals L. And we had in ours, we had a of x instead of f of x. We had the limit as x approaches either infinity or negative infinity of a of x equaled 3. So L is a number that it's approaching. A of x is our function, and that could be whatever function you're dealing with in the problem. So we're going to look at a bunch of different graphs, pick out what are our different limits as we go to positive infinity and negative infinity. So this first one on the bottom of page 5 on the left, our limit as x approaches negative infinity we've got t of x for our function. As we go really, really far to the left, you'll see we are getting closer and closer in our y values to 1/2. Same thing on the right. Our limit as x approaches positive infinity of t of x is also going towards 1/2. So this is a case where our left-hand limits and our right-hand limits are the same value. Or sorry, not left-hand and right-hand, but going to negative infinity to the left and positive infinity to the right. Here's a case where you can clearly see they're different. Our limit as x approaches negative infinity, in this case we're working with g of x. Our y values when we go to the negatives, to the far left, are getting closer and closer to 0. But over here, our limit as x approaches positive infinity for g of x, as we go to the right, we're getting closer and closer to 3. So here's a case, which we saw a couple slides ago, where we're going to have two horizontal asymptotes. One to represent what we're approaching when we go to positive infinity, one to represent what we're going to when we approach negative infinity. If we flip to the next page, our limit as x approaches negative infinity of h of x is getting closer and closer to 0. And our limit as x approaches positive infinity of h of x, well, this is growing without bound. Okay, it's getting larger and larger and larger. Technically, that's a limit that doesn't exist because it's not going towards a number, but we say that it is equal to infinity to denote that it is getting larger and larger and larger. If we have a constant function, our limit as x approaches negative infinity of q of x, well, that's just equal to 3. And our limit as x approaches positive infinity of q of x is also 3. Okay, because it's a constant function, it's always going to take on that same value. Now for this function r of x, you can't see as much of the graph going to the left, but this is actually symmetrical with the y-axis. So the same thing is happening to the left as is going with the right. So our limit as x approaches negative infinity of r of x, and our limit as x approaches positive infinity of r of x is going to be the same thing. And notice our amplitudes in this wave are getting smaller and smaller and smaller, so our function is approaching 4 in both cases. Again, you can't see it on the graph, but the left side of the graph looks exactly the same as the right side. It's symmetrical with the y-axis. Now the next one, we've got a sine wave whose amplitude is always 1. This is not getting closer to any y value. It's constantly oscillating. So therefore, we say our limit as x approaches negative infinity of s of x, and our limit as x approaches positive infinity of s of x does not exist because we are not actually getting closer to a value. Flipping to the next page, two things that sound the same that sound similar but are very different. Infinite limits versus limits at infinity. On the right side, that's what we've just been working with. Limits at infinity. As x approaches positive infinity or x approaches negative infinity, what value is it going to? Over on the right, or over on the left, sorry, we have cases when our limits at certain x values go to positive infinity or negative infinity. So infinite limits are where your function increases or decreases without bound, gets really huge or really huge negatives. Where limits at infinity are when you're looking to see when your x's are getting close to infinity, what values are you approaching? And the graph in the middle just demonstrates these 5 cases that we have listed here. Now, when you have a limit approaching infinity, you can't just plug in infinity, because that could lead to results that aren't quite accurate, because infinity is not a number. What you need to think of, rather, is think of very, very large numbers and plug in really large numbers or really large negative numbers or positive numbers, depending what it's going towards. So our limit as x approaches positive infinity of 1 over x. So in other words, x is becoming huge numbers. So we've got like 1 over 100, then 1 over 1,000, 1 over 10,000, and so forth. As those numbers on the bottom keep getting larger and larger, our overall fraction is getting closer and closer to 0. That's becoming a really, really, really tiny fraction. And now as our limit, as x approaches negative infinity of 1 over x, we're getting really large negative numbers. So we'll have 1 over negative 100, 1 over negative 1,000, 1 over negative 10,000. And even though they're coming from the negative side, they're still getting closer and closer and closer to 0. So each of these limits, as x approaches infinity or x approaches negative infinity, would be 0. And that's going to be the case whenever your denominator gets large and your numerator stays the same, it's going to eventually go to 0. And we've got a similar case here. Our denominator is going to get huge, and then we'll take either a power or a root of it. Well, as the denominator is getting huge, even if you take a root of it, it's still going to be a huge number. So this is still going to be the same thing as before, 0 for each of them, because your denominator is getting huge, your numerator is staying the same. We've got our limit as x approaches positive infinity. Okay, we can treat this just like you did last year. They're both x squareds on both numerator and denominator, so same degree. Just find the ratio of the leading coefficients. So this limit would just end up equaling 3/5. Now we've got inverse tan. Well, let's think about what regular tan looks like. Regular tan has asymptotes at negative pi over 2 and positive pi over 2, and looks something like this. Well, when you graph an inverse function, the x's and y's get flip-flopped. So instead of having asymptotes at x equals negative pi over 2 and x equals positive pi over 2, we'll have y equals pi over 2 and y equals negative pi over 2, where our asymptotes will be located. And then our function will now look something like this for inverse tan. Now from the graph, it's a little bit easier to see what our limit will be. In the first one, as x approaches positive infinity in inverse tan here, our y values are getting closer and closer to pi over 2. And when our x's approach negative infinity, our y values are getting closer and closer to negative pi over 2. And here's just another picture of that makes that clear. Now, this is an interesting case in E. We're going to infinity, so x's are getting huge. When you do 2 times a huge, huge number squared and then add 1, the 1 really doesn't play much of a role, because the number is going to be so huge, when you add 1, it does not affect it much at all. So you can kind of think of this as being 2x square root of 2x squared over 3x. So if you kind of ignore the 1, this is almost like saying square root of 2x over 3x minus 5. Well, now they're both x to the first. Your leading coefficient are now square root of 2 over 3. So your limit here would be square root of 2 over 3, again, because that plus 1, as x's get really huge. When we do 2 times a million squared, if you add 1 to that, big deal. It's not changing the value of it too much. Okay, and here's a visual of what the graph that we had looks like. Moving to the next page with some more limits. Okay, again, don't try and plug in infinity. Think really large numbers. So the one on the left, if you take really huge positive numbers and cube them, you'll get back really huge positive numbers. So that limit would be infinity. If you take really huge negative numbers and cube them, because a negative times a negative is a positive, and then times another negative is still a negative, we'll get really huge negative numbers back. So anytime it's going to get really huge, again, we saw before, we'll just say that that limit goes to either positive infinity or negative infinity if it's going to be positive or negative. Even though that's technically something that doesn't exist, because it's not going to an actual number, we use the infinities to represent that it's getting either huge positive or huge negative. All right, so this, we have the limit of e raised to the 1 over x as x approaches 0 from the left, notice. Well, let's break it down. Let's just look at 1 over x, the limit as x approaches 0 from the left. So let's put in really small negative numbers. That's what approaching 0 from the left really is. So we're doing 1 over negative 1 over 100, 1 over negative 1 over 1,000, negative 1 over negative 1 over 10,000. Well, what these numbers really are, by keep, change, flip, this is really 1 divided by negative 1 over 100, which is really 1 times negative 100 over 1. This is really 1 divided by negative 1 over 1,000, which is really 1 times negative 1,000 over 1. And again, this is just by doing keep, change, flip like you used to do back in middle school. 1 divided by negative 1 over 10,000 is really 1 times negative 10,000 over 1. Therefore, our limit of the 1 over x part, as we go to 0 from the left, these are going towards negative infinity. So we know this part here is going to go towards negative infinity. So we just need to think, okay, what does e to the x do as x goes towards negative infinity? Because really, our exponent is just going towards negative infinity. And if you think of the graph of e to the x looks like this. And as we go towards negative infinity, we are getting closer and closer to 0. So overall, this limit is just going to 0. For h, there's 2 ways you could think of this. One, you could leave it as it is and think of if you take an enormous number and square it, and then subtract off another enormous number, but not nearly as enormous, you're still going to get an enormous number. So it would give you infinity. The way to think of it is pull an x out, and you'll have x minus 1. Well, if you have an enormous number times that same enormous number minus 1, you're still going to get an enormous number back. So that would give you infinity as well. So 2 different ways you could think of it. Square root of x squared plus 1 is very close to being just plain old x. Because square root of x squared would just equal x. Square root of x squared plus 1 is very, 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 very similar. So, for example, we know that 1,000 1,000 squared would just have 6 zeros. We know the square root of 1,000 squared plus 1, that would be the square root of 1,000,001. Well, 1,000,001, when you take the square root, is just about 1,000. Okay, it'll just be slightly bigger. And then you're going to subtract that 1,000 off here, so that's going to be really, 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 really small numbers. And as your x's get huge, the difference between those is going to be insignificant. So really, this is going to get closer and closer to 0. Okay, and here's an illustration of that function to see that it is getting closer and closer to 0. E to the x, as x approaches negative infinity, we kind of looked at that within the other problem. Here's your graph of e to the x, roughly looks like that. As we get really, really far to the left, that's getting closer and closer to 0. Now, something that's true about any exponential function that doesn't have a shift up or down, it's going to pass through the y-axis at 0, 1, and we also have the x-axis, y equals 0, as a horizontal asymptote. And that's something that will be true of our exponential functions that have shifts up or down. If we look at cos x, cos x will look something like this, and then it'll just keep oscillating. So just like the example we saw before, I think we saw sine x plus 4, same idea, this limit will not exist. On top, when you have huge numbers that get squared and then have that same huge number added to it, you're going to get a really huge number. And on bottom, you're going to get negative huge numbers, because 3 minus a huge, huge number is going to be a really, really huge negative number. So one way to think of this is you have a really huge positive number on top, and you also have a huge negative number on bottom. Okay, the reason the bottom's just huge and not really huge is because you didn't have it squared and added to something. Okay, so the top should be significantly bigger than the bottom still. Basically, we're just doing this to figure out if it's positive or negative, because you have a positive divided by a negative, so you know it's going to be negative. The other part of it, we could have just used from what you learned last year. Our degree of the numerator is greater than the degree of the denominator. Therefore, you can't use your coefficients, and it's not going to go to 0. This is a slant asymptote case. With your slant asymptotes, because it was slanted, it was either going to go to positive infinity or negative infinity as it went along those slant asymptotes. We just figured out here, because we're going to have a positive over a negative, it's going to in fact go to negative infinity. Now, here's another way that you can look at it. If you multiplied everything by 1 over x, x squared times 1 over x would go to x. X times 1 over x would go to 1. 3 times 1 over x would go to 3 over x, and negative x times 1 over x would go to negative 1. And we can do that because we multiply the top and bottom by the same thing, so that's like multiplying it by 1. Well, on top, we're going to get a huge number plus 1. On the bottom, 3 over x, that's going to go to 0 because your denominator is going to get huge, and you'll just be left with negative 1. So we'll have on top a huge number plus 1, and on bottom we'll just basically have negative 1. A huge number divided by negative 1 is negative infinity. All right, the last thing for this video is down at the bottom of page number 8. we can find a sketch of this graph just by looking at our roots and our intercepts. Our roots are what are going to make it 0. So 2 will make this part 0, -1 will make that part 0, and +1 will make this part 0. So we can plot each of those. You also learned last year that any even-powered ones are going to bounce. So we will bounce at our +2 root. So that one will get a bounce. Our y-intercept we can get by plugging in 0 for x. When we put in 0 for x, we'll have -2 to the 4th, 1 to the 3rd, and -1. -2 to the 4th will give us 16 times 1 times -1, so we'll get -16 for our y. So we know that we must have to pass through -16. So that means our graph must go down like this. And then the -1 and 1 were odd-powered, so we must have to pass through them. On the left, we don't have any other roots, so we must just go up. On the right, we have a root to come back to, and we're going to bounce it, and then we must head off. So your graph must look something like this. That's all for today's video. We'll see you next class period.